Okay, so back in section 1.1, when we talked about the steps of problem solving, one of those steps was to devise a plan. And there was a whole bunch of ways that we could devise a plan. And one of those was to look at a pattern. Well, patterns are everywhere, right? I mean, we constantly are looking for patterns in our lives, even from like our daily routine. We've got weather, nature, traffic lights. They just show up everywhere. And we're kind of constantly looking for patterns where we can make predictions and have a predictable kind of either schedule or make a prediction about something that's going to happen. So in this section, we're going to look at a whole bunch of different types of patterns. Before we do that, this may look a little bit odd, but we're going to talk about two types of reasoning. We have inductive reasoning, which is drawing conclusions based on collected data and observed patterns. Now, here's the thing. Inductive reasoning may not always be true. Okay? I'll show you an example in a minute. Then we have deductive reasoning. That's using proven facts and logic to validate an argument. Okay? Now, let's go back to inductive reasoning because we said, hey, you're drawing conclusions based on this data and observed patterns. Let's say that you look at 0 squared and you're like, okay, 0 squared is 0. 1 squared is 1. And you stop right there and you say, hey, any number squared is itself. You collected some data, you observed a pattern, and you drew a conclusion. Now, we know this conclusion is wrong, okay? So first of all, this conclusion that you make using inductive reasoning is called a conjecture. Now, this conjecture, you can either prove it to be true by using deductive reasoning, that's using some kind of proven facts and logic to validate this argument, or you can disprove it by one single counterexample. Now, a counterexample is just a big word for an example that runs counter to what you're doing, right? So it's counter to, what you're doing. So here, oh my gosh, where do we even start with a counterexample, right? So I just picked 4 squared. You could have picked 2 squared, 3 squared, pretty much anything else squared is going to show you that this conjecture is not true. So I mentioned before, it only takes one counterexample to disprove a conjecture. Okay. Let's look at patterns inductively. Okay. That means we're just going to make this assumption based on the collected data. We're just going to hope that they're true. So let's find the next 2 terms. So we got the pattern 1, 5, 9, 13, blank, blank. So take a second. See if you can figure out what that next term would be. See if you can find the next 2 terms. You can always pause the video and try to fill that in. Don't just wait for me to tell you. It's actually really helpful if you can figure them out beforehand. So you can pause the video, try to figure out the next 2 terms for all of these before I tell you. Okay, so this one, the pattern is that we're adding 4 each time. Right, so that means the next term, we add 4 to 13, and we get 17. We add 4 again, and we get 21. So there's the pattern. All right, B. This one, you'll notice the numbers are decreasing. So this time, instead of adding, I'm subtracting. And this time, I'm subtracting 5 each time. So 14 minus 5 is going to be 9. And then 9 minus 5 is going to be 4. You can also see that it's a 9-4, repeated pattern in there because of the way that our base 10 system works. But this one's harder because, the first 2 are just adding the same fixed number or subtracting the same fixed number. Part C is a lot tougher to see because you might say, okay, I'm adding 1 and then I'm adding 2. And then I'm adding 1 and then I'm adding 2. So does that seem to continue? Well, let's see. So add 1, add 2. Add 1, add 2. Add 1, add 2. Add 1. So So we have plus 1, plus 2, plus 1, plus 2, plus 1, plus 2, plus 1, plus 2 would make that 13. And then continuing our pattern, plus 1 would make that 14. You don't want to make an assumption too soon. Okay, so you'll notice I didn't just stop right here and say, oh, okay, it's a plus 1, plus 2 pattern. I went ahead and saw it all the way out. Okay, this pattern could also be described as skipping the multiples of 3. So you could look at it like that and say, oh, I'm just skipping the multiples of 3. 3, 6, 9, 12, 15, and so on. All right, then we've got this one, 3, 9, 27, 81. So, okay, you look at that and you're like, okay, I got to add 6, 9 to 27. Ooh, that's a lot more than 6, right? That's like, 18? And then 27 to 81, wow, that's a lot more. So there must be a different pattern happening in there. This one, instead of addition or subtraction, this is a multiplication pattern. I'm multiplying by 3 every time. So 81 times 3 will be 243. And then 243 times 3, I don't know that one off the top of my head. I knew 81 times 3 in my head. That'll be 729. So our patterns can be addition, subtraction, multiplication. They could even be division. All right, this last one, there's a couple of different patterns that we could look at here. You might look at this one and say, okay, so from 1 to 4, I have to add 3. From 4 to 9, 5. From 9 to 16, you add 7. From 16 to 25, you add 9. So you might look at that and say, hey, there's a pattern within the pattern. Right? 3, 5, 7, 9. Those are odd numbers. The next odd number, so after this, because these are going up by 2s, would be 11. So that would make that 36. The next odd number after 11 would be 13. So that would be 49. This sequence right here is also the sequence of perfect squares. So let me just kind of make a little note down here. So if you didn't do this odd addition pattern, the perfect squares are 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on. So remember, squared meaning that number times itself. So 1 times 1 is 1. 2 times 2, 4. 3 squared, or 3 times 3, which is 9. 4 squared, or 4 times 4, is 16. 5 squared is 5 times 5. 6 times 6, 7 times 7, and so on. Okay, the sequences in parts A and B, where I added or subtracted the same fixed number, these are called arithmetic sequences. Right? I know that looks like the word arithmetic, but in this case, the way this is used, it's pronounced arithmetic sequences. And so now we move on to talk about arithmetic sequences a little bit more. Okay, so an arithmetic sequence is formed by, now the definition says adding a fixed number called the common difference to each term to obtain the next term. Now we only say adding because if that fixed number is negative, we know that adding a negative is the same as subtraction. So flipping back here, I can still look at this as adding the same fixed number. I'm just adding -5 each time. All right, so just keep that in mind, that even though this says adding, that number that you're adding could be negative, in which case it's going to look like subtraction. Now, there's a formula that we can use for arithmetic sequences. N here is the term number. So we have like the first term, the second term, the third term, fourth term, fifth term. So let me just kind of add that on there, because that's kind of the term position. A sub n is the notation that we're going to use for the number in that position. So A sub 1 is the first term. A with a little 2 is the notation for the second term. All right. My first term, if I look back at this 1, 5, 9, 13 sequence, the first term was 1. Then I added that common difference, which for that example was 4. To get to 9, I added the difference again. I added 4 again. That's twice that I've added the 4 from the beginning. So what we can do is kind of derive this formula for finding any particular term for an arithmetic sequence. My second term, I add the difference once. The third term, to get to this third term, I had to add that common difference 2 times from the beginning. Remember, A sub 1 is the first term. For the fourth term right here, I had to start at that first term, and then I had to add the common difference 3 times. To get this one, I had to add the common difference 1, 2, 3, 4 times. So you can see the pattern here is that whatever your term number is, you have to add 1 less the common difference over and over again. So the 100th term, we would have to add the common difference 99 times. This gives us this formula that we're going to use a lot. So keep this thing handy. But you got to be able to interpret it. A formula is only really helpful if you know what all the things mean in it. So we have this little A sub n. I say sub because it's a subscript. So that's how that's read. This is the nth term. So if we're talking about the 100th term, that would be A sub 100 or the 100th term. A sub 1 is just the notation for the first term. N is the term number. That's your location, like first, second, third, fourth. And then D is your common difference. 1, that's just the, that nice whole number snugly nestled between 0 and 2. All right, so let's use this. So let's use this to find the 100th term for this arithmetic sequence. So n, in this case, is 100. So let me write this formula. So I have A sub n equals A sub 1 plus n minus 1 times d. All right, so this is my n. And see how that n shows up twice in that formula. A sub 1, there's nothing to find, no work whatsoever. It's just the first term. Boop, right there. It just so happens to be 1. It's not always 1. It's just whatever the first term is. And then D is your common difference. It's that number you're consistently adding each time to get the next term. In this case, it was 4. Okay, so we get A sub 100 equals my first term. So that first term right there is that 1 plus n, in this case, is 100 minus 1 times D, which is 4. So there's multiplication right there. Now, just break out the calculator. So let me just make a little note to you that we're just going to use the calculator so you don't think something, super complicated is going on here. And you're just going to type it in exactly like it looks, okay? So you're going to do 1 plus parentheses 100 minus 1, close parentheses, times 4. Now, most calculators, you don't have to put the times. It knows that that's multiplication by those parentheses. Just habit of my own. All right, so I get 397. So I have A sub 100 equals 397. There we go. That means the 100th term of this sequence is 397. Now, it probably goes without saying, but I'm going to say it anyway. If I were to ask you this on a test and you just kept listing these out and you counted to 100, I'm not giving you credit for that. Also because that would require me to kind of check that out. And if you make a mistake, I'd have to find it. And I'm not counting 100 terms out and making sure you added 4 over and over again. I'm not about that life. So this is a shortcut for us, because also, what if I ask you the 300th term? I hope that you just kind of see the merit in this. You're like, yeah, you know what? I wouldn't do that anyway. So, all right. Let's use this formula that we just used, but let's use it a slightly different way. Sorry, I just bumped the tripod, so if it kind of got all a little wobbly there for a second, that was me. All right, how many terms are in this arithmetic sequence? Now, for this one, we are going to use that same formula right here, but if we want to know how many terms, we're going to be solving it for n. So we're going to use this formula, but instead of doing it very straightforward, like we did here, where we just plugged in, used the calculator, done, now we're going to have to use a little bit of algebra. Okay, so we're going to use this formula, a sub n equals a sub 1 plus n minus 1 times d. Now, let's go ahead and figure out this sequence, what we can plug in, knowing that we're looking for n. So how many terms is going to be n? So we're solving for that. That must mean we can plug in for all the other variables. All right, remember, a sub 1 is my first term. Now, that just right here, just the first term, that's it. Boom. A sub n, in this case, is my last term, because I want to know what term number is this. Is this the, 900th term? Is it the 50th term? So this one is right here. For a lot of these, this will be your first term and this will be your last term. All right, we're solving for n, so don't plug anything in for n. You don't know that one yet. And then we have d, the common difference. This one, remember, we did this one back a couple pages ago, and that common difference was that minus 5, that subtraction of 5. So we have that my common difference is negative 5, and that was from example 1, part B. All right, so let's plug in. So we get negative 401, don't forget that negative sign right there, easy to miss, equals a sub 1, 29, the first term, plus n minus 1 times d, which is negative 5, because I was subtracting 5 each time. So that's times negative 5. All right, now you need some algebra skills for this one. But don't worry, we don't have a whole lot of algebra in this class. So if you feel like your algebra skills are a little weak, that's okay. We'll work our way through them together, okay? So with this, I'm going to start by distributing this multiplication through these parentheses. All right? Don't multiply this negative 5 times 29. It's only being multiplied by these two things inside the parentheses. So let's distribute that. So we get negative 401 equals 29. Now, negative 5 times n is negative 5n. Well, here, I'll tell you what, let me go ahead and just write it. So plus negative 5n plus, from right here, negative 1 times negative 5. All right, a negative times a negative is a positive. So that'll be plus a positive 5. If you need to use a calculator just to make yourself feel better about it, you can. This right here, this plus a negative, we can write this nicer. we can just write this as just minus 5n. We don't have to write that as plus a negative and have it be a little messier looking. All right, we can combine these two constants because they're on the same side of the equal sign. I can't combine all three of these numbers because that one has a variable and these are constants. They're not like terms. But these two are like terms. But all three of them together are not like terms. Okay, so 29 plus 5. So we get that negative 401 equals 34. And then we still have that minus 5n. All right, we've got this down to what we call a two-step equation. This 34 can be combined with this constant over here because they're like terms, but they're not on the same side of the equals. I have to move them to the same side. So my goal is to get the n by itself. So let's move this one away from the n. It's a positive 34 because there's no sign there. So I'm going to subtract 34 from both sides of the equation, both sides of the equal sign. That will zero out. Don't forget that sign. So that's a minus 5n. This is negative 401 minus 34, or negative 401 plus negative 34, however you want to look at it. So together, those combine to be negative 435. And then lastly, because that smushing right there is happening, that's negative 5 smushed up against n. That's multiplication. So that is implied multiplication. You can't add 5 to both sides here because that's not subtraction. That's a negative number times n. So to get rid of this number with n, I have to divide both sides by negative 5. Now I know it looks like a fraction, but this is just the notation for division. So here, let me put a happy little thought cloud on there. So let's say, hey, that fraction bar right there means the same thing as that division symbol. So just grab the calculator. We have negative 435 divided by negative 5, and we get 87. Now, notice this is your negative sign. This is your subtraction. If you try to do the subtraction sign for your negative, it'll automatically bring up answer because that means you're trying to subtract something. So it gives you something to subtract from. If you did negative 435 divided by subtraction 5, it'll give you what's called a syntax error. That means it doesn't understand what you're typing. So if you use a little arrow here and you go to, look, it's blinky blinky on that. It's telling you that's the problem. I don't understand what you want from me. So you would just have to change that to a negative sign. It's a very subtle thing and an easy mistake to make. So I just wanted to go ahead and address it just in case it happened to you. All right, so we got 87 equals n. There we go. That means that this negative 401 is the 87th term. So I do want you to use this formula. I don't want you to fill in all of the gaps here and then count them out, right? That's absolutely not what I'm asking for you. Also, this ... means that the pattern continues until you get to here. I've seen students who will just ignore that and say, oh, there's 1, 2, 3, 4, 5 terms. Like, no, there's a lot more. That ... means the pattern continues until you reach this term. So don't dismiss the ... And don't try to fill it in with everything. That would take too long, because what if this, instead of being 87, what if that had been like 5,087? I mean, ooh, you'd be there a long time. Okay, moving on. Find the sum. Now, in section 1.1, we used the Gauss method, right? Where we paired up, you know, the first and the last, and then the second from last and stuff. This is one where we could use the Gauss method, but it gets really messy, okay? The Gauss method does work on any arithmetic sequence, all right? Because of that, we can actually make kind of a formula out of it, right? We can use this shortcut formula. This S sub n is the sum of the first n terms of an arithmetic sequence, the A being arithmetic. We have the same n, which is the number of terms, right? The position, first, second, third, fourth. So the sum of the first n terms is n over 2 times the quantity a sub 1 plus a sub n. Remember, a sub 1 is your first term, a sub n is your nth term, but typically when we're using this, it's my last term. So yeah, I'm just putting that out there. So rather than trying to pair these up, and this gets messy because like with this, how many terms are we adding? Because with Gauss, it's like, oh, okay, I'm just going to pair them up and then take the total number of things I'm adding and split it in half, and that's how many pairs I have. It's not obvious how many numbers I'm adding up here. When I was doing this in section 1 and we added 1, 2, 3, 4, 5, all the way up to 100, then it was a little more easy, right? You're like, okay, I'm adding up 100 numbers. There you go. Here, that's not so easy. So you might notice that my lab might encourage you to try to use the Gauss method, but I'm giving you a shortcut instead. Okay, before we can use this formula though, we need to know n, the number of terms. We know the first term is 2. We know the last term is 296, but we don't know how many terms there are. So we need to know n. We can find this using this formula right here. Right? So we got 2 plus 5 plus 8, da, da, da. There's my first term. There's my last term. My D, my common difference, is 3. Right? 2 to 5 is 3. 5 to 8 is 3. So that's what I'm about to plug into here and solve for n. So you can kind of see the progression that I'm using this formula for. Right? Okay. So we have a sub n equals a sub 1 plus n minus 1 times d. There's my formula. So if I start plugging in stuff, I've got 296. A sub 1 is 2. N is what I'm going to be solving for. And my common difference right there is 3. This is very similar to the last example I did where we're going to have to use a little bit of algebra. So I am going to distribute that 3 throughout. I'm at the bottom of my page, so I'm going to go to the next page. I knew I was going to have to do this, so you can see I've got a blank page in there. So I'm going to distribute that 3. This is going to be a little easier than the last one because I don't have a negative to distribute. The negative distributing is slightly harder, but okay, so I get 296 equals 2 plus, I'm just going to rewrite it here because I can. All right, so I'm going to distribute that 3 throughout there. So that's 296 equals 2 plus 3 times n minus 3 times 1. So 3 times n is 3n. 3 times 1 is 3, and that minus right there carries down. Just like last time, you'll notice these all solve the same way. Just like last time, I'm going to combine those like terms. Now that's a 2 and a minus 3 that's being added together. So those are going to combine into a minus 1. So that'll be a 3n minus 1. I'm going to get rid of this constant and combine it with this by moving it to the other side. It's a minus, so I'm going to add 1 to both sides. So I get 3n equals 297. And just like last time, my last step, because that smushing right there is multiplication, my last step is going to be division. So I need to take 297 divided by 3. 297 divided by 3. Now, something to keep in mind when you're doing this, because n is your term number, right? First, second, third, fourth, fifth, blah, blah, blah. This should be a whole number. If you get a decimal, if you get like 99.7, you did something wrong. It should be a nice whole number. It should also be positive. So just keep that in mind. So I got 99. Okay, now that's not my final answer. We'll go back. I want to find the sum of this sequence. I need to use this formula right here. All right, so the sum is S sub n equals n over 2 times the quantity a sub 1 plus a sub n. Now I've got my n value of 99. All right, I'm looking for the sum, that sum of the first 99 terms. That is 99 divided by 2. Now, a sub 1 plus a sub n. Let's go back. Remember, a sub 1 is your first term. A sub n is your last. There's my sequence. My first term is 2. My last term, oops, keep bumping that tripod, is 296. I'm going to end up with some motion sickness if I keep bumping that tripod. All right, let's bust out the calculator here. So I'm just going to do what's in the parentheses first. So that's going to be 298 times the quantity 99 divided by 2. I did tell the calculator that that was its own fraction, that 99 over 2, by putting it in parentheses. All right, so we get that sum of the first 99 terms is 14,751. All right, I know I've said it before, but I'm going to say it again. If you try to fill in this ... with all the other terms, and you list out all 99 terms, and then you just bust out the calculator and start adding those up, I am not following you on that journey. All right, I'm just going to go ahead and say it. We're not going on that journey together. You were alone on that journey. The whole point of this is to use these formulas, in the correct way, and in this point, in this example, in the correct order. So formulas are great. You just have to know when to use them and how to use them. All right. So all of that was just for arithmetic sequences. So let's move on to a different type of sequence. Next up, we have geometric sequences. So remember, arithmetic sequences, we were adding the same fixed number over and over again. Geometric sequences, we are now multiplying by the same fixed number, but now we can't have 0. It's got to be a non-zero number. That's because if I multiply by 0, the whole sequence just zeroes out, right? We just get 0, 0, 0, 0, 0. From example 1D, we had this sequence where we multiplied by 3. So that would be a geometric sequence. Now, this same fixed number, this common ratio that we're multiplying by, can be positive, it can be negative, it can be a fraction, it can be a decimal, but it can't be 0. So it's not going to be 0. All right, so now let's kind of pull this together with the arithmetic sequences. So I'm going to give you a bunch of sequences. Let's identify them as either arithmetic, that means adding the same fixed number, could be positive, negative, or 0. Geometric, multiplying by the same fixed number, or neither. It doesn't have to be one or the other, it can be neither. So pause the video and see if you can just go through and identify those as either geometric, arithmetic, or neither. All right. So we're going from 18 to 30 to 42 to 54. Well, let's start with arithmetic because it's the easier one, right? So 18 to 30. If it's not obvious to you, you can always subtract. So we take 30 minus 18 and we get 12. Then we do 42 minus 30 and we get 12. And then 54 minus 42. There's a reason that in the arithmetic sequence formula that D is called a common difference. It's the difference between each term. So subtraction there implying some kind of difference. So you can always find that difference by using subtraction. Okay, so this one is arithmetic. And my common difference let's see, I'm adding each time, and I'm adding 12. So I did that subtraction to work backwards to help me figure out what number I was adding. Now I did that just in case, some people can do this in their head and just say, oh, I know from 18 to 30 is 12. And then, so if you're really solid with your arithmetic and you can do that in your head, that's awesome. All right, this one, let's see. 1 to 3, that's adding 2. All right, that's adding 3. That's adding 4. That's adding 5. All right, so that's plus 2, plus 3, plus 4, plus 5. Now, you might say, okay, I'm adding each time, so it must be arithmetic, right? Arithmetic add. But you're not adding the same fixed number. That's key, right? In arithmetic, you're adding, of course, but it's the same number. Here, I'm not adding the same number. This is neither, because I'm not adding that same number throughout. So I did that on purpose because I didn't want you to think that addition means arithmetic. It does if it's the same number that you're adding over and over again. All right, so this one, let's see. If I had to add to get from -3 to 6, I would have to add 9. And then 6 to 12, okay, that's not 9, so it's not arithmetic. Well, 3, 6, 12, 24, kind of see some multiplication maybe happening in here. So from 3 to 6, I had to have to multiply by 2, but now we got to remember our sign rules. So multiplying right here, I would have to multiply by -2, because that -3 times -2 is a +6. A negative times a negative is positive. Again, if I multiply by -2 again, 6 times -2 is -12. Positive times negative is negative. And if I multiply by -2 again, -12 times -2 is a +24. This is multiplying by the same fixed number, so it's geometric. My common ratio is -2. It's called a common ratio because if I take the ratio or the division of successive terms, of adjacent terms, I get the same number. So 24 divided by -12, -2. -12 divided by 6. So take any term and divide it by the one right before it, and you should get the same number. That's why it's called a common ratio. All right, next up, 5. All right, well, you might say, oh, well, I'm just adding 0 every single time. So it's arithmetic. And my common difference is 0. But get this, you could also say, oh, no, it's also geometric. So let's put an and sign. Because it's also geometric, and my common ratio that I'm multiplying by every time is 1. Constant sequences like that aren't all zeros are always arithmetic and geometric. So it is possible to be both. All right, then they start getting really messy, right? Now it starts getting, really, really hairy here. These fractions are going to be a mess. So you might have to use the calculator to help you with those. All right, so like I showed you before, that we can take any term and divide it by the one before it. This is a little messier though, because of the fractions. So let's take 3/8 and divide it by the one before it. Notice when I'm doing fractions, I'm using division, and then I'm putting them in parentheses just to tell the calculator that they're grouped together. All right, so I got 0.75. Let's see if that keeps happening. So 9/32 divided by the term right before it, which is 3/8. Oh, 0.75. Okay. let's check the last one. So 27 over 128 divided by 9 over 20. Oh, nope, 9 over 28. Oop, 32. Almost messed that up. 0.75. This means that it is geometric, and my common ratio is 0.75. Now, you can write it as a decimal, or if you need to change this to a fraction, you can hit the math button, and that first thing right there has a little arrow to fraction. You hit enter once, it brings up the command. Enter a second time will execute the command. And so that'll change it to a fraction of 3/4, just in case you need the fraction version. Now, my 84 Plus is a little old, so it does not have this feature on it, but some newer 84 Pluses will have a fraction built in. It is under alpha and then the y equals. So mine doesn't have it, but some of them, if you hit alpha and y equals, it will bring up this little hidden command box that has fractions in it, which is so awesome. So if your calculator has that, feel free to use that feature. I'm just going to use division on this because my calculator is old, but I love Pinky anyway. Okay, next up. Now, I just did geometric, so this one's probably not going to be geometric. So let's see if this one's arithmetic. Now, if it's arithmetic, I'm adding the same fixed number. That means that if I take any term, so I'm going to take 7/4, and I subtract the one before it, I should get the same fixed number. All right, so 2 minus 7/4, and then 9/4 minus 2. So you can see that by taking any term, subtracting the one before it, I keep getting the same fixed number, 0.25. Now, 0.25 is the same as 1/4. This one is arithmetic, and my common difference is 0.25 or 1/4. I was about to run into my 3/4. I got a little wild with it. All right, G came to me from a student who, I forget what kind of test she was taking, but she sent this to me and was just lost. She's like, I have no idea what to do with this. And I had to look at it for a bit too. So look at this one, 1 to 1. There's no change, right? Then we go 1 to 2, and then 2 to 6. So look, from here, we go times 1, and then 1 to 2, we go times 2, and then 2 to 6 times 3, and then times 4, and then times 5. So it's a multiplication. So it's kind of like this one up here, but it was a multiplication pattern in there. But because we're not multiplying by the same fixed number, it's not geometric. So it's neither. In order to be geometric, it's not enough to just multiply. It has to be the same number that we're multiplying by. I've also seen sequences that mix multiplication and addition together, so those get a little crazy too. All right, 9, 7, 5, 3, 1. So it looks like from 9 to 7, we have to subtract 2. And then 7 to 5, we subtract 2. 5 to 3, we subtract 2. All right, so ending on a nice, easy one. That one's arithmetic, and my common difference is a -2 because I'm subtracting that same fixed number every time. All right, so other sequences. So we've talked about the arithmetic patterns, the geometric patterns. Let's talk about some other ones. Figurate numbers. We have triangular numbers, 1, 3, 6, 10, 15, and so on. Those are called that because the number of dots that coincide with these numbers form a triangle. So look, 3 is a 2, 1 triangle. 6 is a 3, 2, 1. 10 is a 4, 3, 2, 1, and so on. Then we have the square numbers, like 1 squared. Remember that one back from example 1? 2 squared, 3 squared. And look, when we say squared and we think of the little 2, the elevated 2 symbol, that actually means the same as this shape, this geometric shape. 9 is 3 squared because it's a 3 by 3 square. 16 is a 4 by 4 square. So those are what's referred to as figurate numbers. All right, so let's look at this triangular number one because we do use these a lot. Let's find the 250th triangular number. Now this pattern, 1, 3, 6, 10, 15, is not arithmetic, right? We add 2, we add 3, we add 4, we add 5. It is not arithmetic, so I cannot just use this with 250. So I'm forced to look for a different pattern. Okay, here's my triangular numbers. So just to show you how they're built. The first one is the number 1. The second one, the second triangular number is the number 3. It comes from 2 on the bottom and then 1 on the top. So 1 on the top, then 2 below it. The third triangular number, which is 6, is 1 on the top and then 2 and then 3, or 3, 2, 1, however you want to look at it. So if you just look at each row, you can see that the fifth one is 1 plus 2 plus 3 plus 4 plus 5. So if you add all of that up, you're going to get 15. That means the 250th triangular number is 1 plus 2 plus 3 plus 4 all the way up to 250. Now, this pattern is not arithmetic, but this one is. In fact, you could use Gauss for this, that pairing up thing that we did in section 1. So to add this one up, we could use Gauss, but instead let's use that sum formula. That n over 2 is, times the quantity a sub 1 plus a sub n. This 1, 2, 3, 4 all the way up to 250 is arithmetic. So there's my first term of 1. My last term is 250. Now, how many terms are in this list? Well, that's pretty easy because they're going up by ones. All right, 1, 2, 3, 4. How many things are here? 250. It's when we start skipping that it's harder to determine how many things are in the list. Okay, so a little plug and chug, and I went ahead and just did it to save us a little bit of time. So just use the calculator here, and we get a sum of 31,375. That means that is my 250th triangular number. All right, and then last up is something called a Fibonacci sequence. Now, a Fibonacci sequence is any kind of recursive sequence that's formed by adding the 2 previous terms to get the next term. So, for instance, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. It was, I don't want to say invented, but it was kind of discovered by watching the reproductive rates of rabbits, supposedly. I don't know. That's just what I've been told. Now, just something to keep in mind is that this is the original Fibonacci sequence. If you see anything like in MyLab or something that says a Fibonacci-like sequence, it just means it's the same kind of technique of adding the 2 previous terms to get the next term. This one is the actual Fibonacci sequence. It starts out with 1, 1, 2. That's the Fibonacci sequence. Anything Fibonacci-like is any other sequence of numbers that has the same kind of technique of adding the 2 previous terms to get the next term. So I want to say that maybe one of those shows up in the homework, but you may actually see it again in this course, because patterns are just going to kind of keep showing up. So, okay, so that finishes us up for section 1-2.